Okay, so what we've done up to this point so far is to cover what are the properties of pure components, what are the fundamental principles of thermodynamics, and how do we calculate state changes. So in the homework we covered calculating changes in enthalpy, changes in internal energy, changes in entropy, right? And so the only thing that we haven't covered is state changes of real systems. But we have the equations for that, right? Those big annoying du is equal to blah, 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 dt plus something, something, dv, right? So if we had a real equation of state, we could implement that. So what we're going to do as sort of a combination of introducing more advanced equations of state, we're also going to introduce equilibrium. So now we're going to be talking about multi-phase systems. And today we're going to cover what are the criteria to know when we are in a multi-phase. Sorry, what is the equilibrium criteria for multi-phase systems? How do we know that the system's in equilibrium? And how can we use that to then solve equilibrium questions? Okay, so what we're going to do then is equilibrium criteria. So just as we started sort of all of our other derivations, we're going to draw some sort of an arbitrary system that's going to be useful for talking about our equilibrium criteria. So we're going to draw a large chamber that's divided into two sections. We're going to call this one section side 1, side 2. It's going to have N of 1, V of 1, U of 1, and S of 1. So all the normal properties that we would expect. So at the moment, we're starting with a completely assumption-free framework. We don't know what are the contents of these two phases. We don't know, what the temperatures are, what the pressures are. All we're saying is that we can exchange N, V, U, and S in between the two of them, but the universe itself is completely isolated. So we're going to rely on the second law to basically say at constant U and V, equilibrium is established at S is equal to a maximum. So mathematically we can write this as ds is equal to 0, and also that d squared S is less than 0. That's how we know we're at a maximum point. So if you recall, when we were talking about the stability criteria, we have S as a function of any variable. It has to follow a shape that looks like this, where we know that this here is the equilibrium point. If entropy had a shape like this, right, we still have a criteria down here where ds is equal to 0, but this is unstable. Right, any small perturbation in the system will cause a increase in entropy, which will then sort of rapidly shoot up and go to a maximum state of entropy. Okay. So what we're going to do is we're going to take our system and we're going to apply our mathematical criteria of entropy is equal to a max. So ds is equal to 0 and d squared S is greater or less than 0. So we'll expand S with respect to U, V, and N. So if we do it for one side, ds of 1 is equal to ds dark because it's an open system. And it should be no different for the second chamber. Okay, these expressions here. I would argue they're not particularly useful from a practical perspective. So we need to find a way to transform these partial derivatives into something that we can actually measure to know when we're at equilibrium. This first one is pretty easy to take care of. This is just a definition. ds du at constant v is equal to 1 over t. That's just one of the thermo-identities that we've already derived. This one over here, again, is also sort of a thermo-identity. ds dn at constant u and v is minus g over t. Now, I don't know how many of you have your handout, the useful equation sheet, but this one is one of the ones right at the bottom there. ds dn is equal to minus g over t. Now for this middle one, we're going to have to transform it and play around a little bit more with this. We're going to use the triple chain rule in this. So the chain rule expansion is where we transform, we change the variables around. Well, it's better just to show instead of me trying to explain it. ds dv at constant u times by du ds at constant v times by dv du at constant s is equal to minus 1. And so how I always remember this one is you just kind of rotate the variables around and just do that for every one, and as soon as you've done a full cycle, it's equal to minus 1. So we didn't go over the derivation of this rule, but you can basically do it just with the chain rule and a little bit of algebraic rearrangement. Okay, so from here, we can write that ds dv at constant u and n is equal to p over t. That is because this term here is equal to t, and this term here is minus 1 over p. So let's apply our equilibrium criteria. ds is equal to ds of 1 plus ds of 2. We have 1 over t1 plus 1 over t2. Oops. Okay. Okay, so we're going to do some total balances. So we have a closed system. So that means dn, which is equal to dn1 plus dn2 is equal to 0. So that we have dn1 is equal to minus dn2. Meaning if anything moves from one chamber to the next, right, that's all that happens. We have rigid walls. That means dv is equal to 0. Same that, so dv1 minus dv2. And isolated. And now we're just going to simply substitute everything together. Okay, so now we have to find a way to satisfy this equation under all circumstances, and then we know we're at equilibrium. So in order to do that, we have three different forms of equilibrium. One, thermal equilibrium. Where T1 is equal to T2. That will allow for this term to go to 0. We have mechanical equilibrium. Where P1 is equal to P2. This term goes to 0. And lastly, we have chemical equilibrium. This term goes to 0. So we have made absolutely zero assumptions about anything going on in our system, right? What we've done is we have constructed some sort of a chamber here that is, I think, very appropriate to have. So imagine this is a jar with water, vapor, and liquid water inside of it. So all we're saying in this calculation here is that we're not allowing mass to enter or leave the jar. We are not allowing heat to go in and out, right? We're not allowing the jar to expand and contract. But apart from that, everything else is totally valid on the inside. So what it's saying is that in order for two phases that are in contact to be in equilibrium, these three criteria need to be satisfied. So across any phase change, temperatures are constant. pressure is a constant, and Gibbs free energy is constant, which is sort of what we already knew, basically. This should be a recap of what we already know from basic chemical equilibrium. Temperature and pressure being constant, that makes a lot of sense, right? But the Gibbs free energy being constant, this is what we're going to use sort of as a gateway to solve basically all of our phase equilibrium problems. But we already knew that when you vaporize water, right, the temperature stays constant of boiling water. This is because of the entropy criteria for equilibrium. And in order for entropy to be at a maximum, you have to have the temperature and pressure be constant. So no assumptions going on here. This is just the basic principles and application of the second law of thermodynamics. Okay, any questions? So what now we're going to do is we're going to play around a little bit more. And we're going to say, instead of having the entropy equilibrium criteria, that was for an NVU system. Now we're going to do it for an NPT system, which is what we really care about, constant pressure, where the walls can actually expand and contract. So for an NVU system, S is equal to a max. That's our equilibrium criteria that we just used to solve that problem. We care more about an NPT system. What is the equilibrium criteria in an NPT system? So from that, we're going to start off with the first and second law, du dt. So this is my first law, which I've simplified it down from du dt is equal to summation from our general starting point. So N, which means there's no material entering or leaving, because in an NPT system, number of moles is constant, nothing's coming in, nothing's coming out. And we're going to get rid of the work term because we don't need to needlessly complicate ourselves with having some sort of an impeller or turbine in there. Okay, we're going to write down the second law. The only thing that we left out here of the second law was the flow rate in and flow rate out. Again, because we have that constant N term. So I rearranged solve for Q. The only thing that I did also in addition is I moved the T to the inside of this derivative. It'll make sense why we did that in just a bit. And again, I'll do the same thing up here, but with the P. So if we substitute these two equations together using the Q term as the shared variable, what is that equal to?
Gibbs energy.
Gibbs energy. Okay, so if we look at this equation here, we know that T has to be greater than 0. S gen has to be greater or equal to 0. That tells us here, therefore, that minus ts dot gen always has to be greater than or less than 0? So at equilibrium, dg dt has to be equal to 0 because everything has to be 0 with respect to changes in time, right? Because you have to be at that equilibrium state. It should be time invariant, infinite time. Because of temperature and S gen, that means we know that dg, or that entropy, has to be convex. So if you look at the Gibbs as a function of time or any other variable, the Gibbs has to look like this. That's our equilibrium state. So to recap really quickly, I should put it up here. We'll fill this in. G is equal to a min. And for an NVT system, does anyone want to venture a guess what function determines equilibrium in this system here? It's very common in sort of molecular simulations, polymer calculations. Yeah. Helmholtz free energy. So if you ever look through the thermodynamic literature, and one of the goals that I want everyone to walk away with from this class is that when you pick up a paper that talks about a thermo model, so it could be some stat mech model, could be a molecular simulation, could be a bulk classical thermodynamic model. I want everyone to recognize, why do some people work in G and some people work in A? What's the difference? The main reason here is that when you work with a liquid, you typically assume that the volume is constant. So for liquid phase behavior calculations, it's generally easier to work in the NVT ensemble and minimize the Helmholtz energy. When you have vapor-liquid equilibrium, the volume changes significantly so that the pressure is held constant, and that's why you always work in Gibbs free energy. And in the NVU system, you'd have to sort of look into more of a molecular simulations type paper. It's not necessarily going to be one that you're going to be building a chemical plant around. But for fundamental sort of phase behavior and physics calculations, the maximum entropy criteria is a really commonly used one for stat mech calculations as well. So for deriving theories and things like that, the NVU system is really useful. But in terms of actual practical solving, Gibbs min and A min are the more common of the two approaches. Okay, no assumptions whatsoever. Right, so this shouldn't necessarily be shocking news, right? But what we're doing right now is just going through, dotting all of our I's, crossing all of our T's, and redeveloping all of the thermo that we should know, hopefully filling in all the gaps of maybe sort of the theoretical approach to get there. Okay, any questions so far? So what we have applied so far is that we have applied that ds is equal to 0 to get equilibrium criteria. What we're going to look at now is d squared s has to be less than 0, which means it is concave. And we're going to derive some stability relationships. Right, so we know that the entropy with respect to any variable. Could be time, could be temperature, could be pressure, could be volume, whatever the case is, it always has to be concave. If it is not, then the universe is critically unstable. If the function looked like this, any small change in any fluctuation of any property would cause the entropy to increase. And so it would be sort of an explosive chain reaction. Yes?
And then because spontaneous reactions maximize entropy, so the entropy would just like run away up one of those like hills.
Bingo.
Okay.
So entropy has to be concave, but I'm sure that's something no one's heard in any of their undergrad thermal classes. Yeah?
Also, I mean, I guess that would mean that you couldn't really like lower the temperature or something because if, you know, to lower the temperature, then yeah, you're increasing total entropy, but you're decreasing entropy of a single item. So if entropy had to go up always, then you cool something that actually heat up.
I have to think a little more about that one. You may be right, but I have to think a bit more about that one.
Or just maybe change pressure. I mean, if assuming pressure's on.
Yeah. But ultimately, though, the takeaway from this is that this has to be true, otherwise the universe will just fall apart and crumble to the ground. So what we're going to say now is, okay, what are the implications of this? So we could take the same approach as what we did before, you know, applying this ds is equal to 0 to the d squared s. I'm not going to do it. I'm just going to start the process to show you how it's done, because it is exceptionally unruly. So if we take ds of 1, using the same system that we had before, is equal to ds1 du1 at constant n and v we can do the same thing for ds2. Now we want to apply this criteria, d squared s is less than 0. Okay, so what makes this exceptionally unpleasant, right, is that this right here is a capital, not capital, but like a total differential. It's not a partial differential, which means that this means we have to expand it with all variables. Okay, so I expanded ds1 up here with respect to all variables, and I got 3 terms. Which means now I have to expand each one of these 3 terms with 3 additional terms. So that means this ds1 right here is going to have 9 terms. 3 here, 3 here, 3 here. Right, so I have to expand this one again with respect to u, v, and n. I have to expand this one with respect to u, v, and n, and so on here. Then I have to do the same thing for ds2. Then I have to do the same thing where I substitute, you know, dv1 for dv2 and all that kind of stuff. So we have a big, long, messy equation with about, I guess, what, 18 different terms in it? So we're not going to do that. But we'll just jump to the conclusions. The conclusions for the stability criteria are pretty nice. One is that C sub v has to be greater than 0. never have a negative heat capacity. That as you put energy into the system, its temperature must rise. Totally reasonable conclusion. The other important conclusion is that dP dV at constant T is less than 0. This is going to be a very important relationship for us. As the pressure goes up, the volume must go down. It doesn't matter if we're talking about a solid, liquid, gas. We've made no assumptions at any point in this class so far. So why this becomes so important is when we talk about phase changes using equations of state. Should we go to the next slide here? So the whole reason why we can use a cubic equation of state to predict phase behavior is because of this stability criteria. Let's say, for example, we're talking about the ideal gas law. Let us all take a moment and test. Is it stable? So I'll leave it on you guys. So take a couple moments and do some number crunching and calculate dP dV at constant T for the ideal gas law. Are there any conditions under which the ideal gas law is not thermodynamically stable? Meaning, does it ever violate this rule? So take a moment, try it out. We will be doing a lot of partial derivatives. Well, hold tight, let everyone else catch up. I will call on a random student for them to give me their partial derivative for the ideal gas law, the dP dV. Okay, who's still working on it? Everyone's got it? All right, Joshua. You still working on it? Okay. Okay. You got it?
Yeah.
Okay, so what is it? So dP dV at constant T is equal to?
Negative N RT over V squared.
Very good. One change that I typically like to write for these derivations is I like to do PV equals RT as opposed to PV equals nRT. Just simplifies things a little bit, but basically the conclusion's the same. So you can also write this as minus RT over V squared. So I think something's a bit different here, but the conclusion is the same. So R has to be greater than 0, T greater than 0, V greater than 0. Therefore, dP dV at constant T for the ideal gas law is always less than 0. So it's stable. It's very good. So if we were to plot out the ideal gas law on a P versus, I'm sorry, PV curve, not P versus T. PV curve. And we're going to plot out isotherms. In this case, T is equal to a constant. So what I always like to do when I have to do any sort of plotting or partial derivatives, I like to rearrange the equation so it looks kind of like, what I'm used to seeing in terms of, general algebra. So P is the y variable, RT over V. So what does this function look like? Yeah, it's like a radical. Looks like this here. So the slope at any point in space here is negative, which is good. That's the stability criteria that we care about. But here's the downside to the ideal gas law. It can never predict the existence of a liquid. So the key thing is, how do we actually generate a liquid? We need something different. And that's where cubic equations of state were developed for. Cubic equations of state have a very unique feature that allows the existence of a liquid to be predicted. Now, it's not saying that the cubic equation of state is like 100% perfect. But again, I really like to stress that in thermo, we're really teaching the system. Right? This is a system that people have established that seems to work really well. And it's an equation that we can tune. That doesn't necessarily mean that everything is 100% perfect. And we're going to expand on this on Friday as well. So in a cubic equation of state, at low pressures and high volumes, we get ideal gas behavior. But as you reduce the volume, or you increase the density, and you reduce the pressure, actually no, pressure doesn't really matter. The main thing is the volume. Oops. So as you reduce the volume and increase the density, you're going to be increasing the interparticle interactions. So it's going to behave less and less like an ideal gas and more like a real fluid. So its behavior should be expected to deviate from the ideal gas law. In a cubic equation of state, it will begin to first have a little bend like this, and then eventually we'll have a full-blown dip like this. So this region here is kind of like a real fluid. So, does anyone want to venture a guess as to what this point is right there? Not quite. It's only one point. It's got a specific temperature, it's got a specific pressure, and its volume, and it's got a specific pressure. Critical point. So in a cubic equation of state, there are regions that are unstable. We violate the stability criteria. That region is right there. We'll talk a little bit more about this when we get more in depth into the theory of phase transitions, but this is actually called the spinodal region. And in the spinodal region, you have an unstable fluid. We're going to talk about this on Friday. On Friday, we're going to define the binodal region here. The binodal region is the two-phase region. Now, these are terms that you will see very commonly if you dig into the thermodynamic literature. And I suspect that many of you in your research will have to dig into some thermo papers at some point. And I promise they will seem like they're speaking a completely different language. You know, even after teaching the class, I pick up a thermo paper and I'm just like, okay, you know, what are they actually talking about again? Right? Because they define everything based on these binodals and spinodal regions. But we have to know exactly what they mean in order to really interpret what's going on with them. So, in this particular drawing right here, if we were to draw a line, a horizontal line across these regions here, these are the vapor pressures. So the cubic equation of state can be used to predict phase equilibrium. And that's why they're so powerful. We don't, as chemical engineers, we're not necessarily as concerned with more accurately predicting the density of the gas as a vapor or a liquid, which is very important for some fields, right? I'm sure in reservoir engineering it's really important to have an accurate equation of state because you want to know what are the PV relationships down the well. But in terms of a chemical plant or a refinery perspective, we mostly care about using equations of state to calculate phase equilibrium and calculating the Gibbs free energy. So in that sense, the cubic equation of state is extremely powerful because it has this region of instability here. Now what we're going to be talking about on Friday is how do we actually identify how to draw this line and know what are the bounds of our spinodal region, the bounds of our binodal region, and the definition of what our vapor pressure is. So with the cubic equation of state, we can calculate what is the vapor pressure, what is the two-phase region. And then with mixing rules, we can use a cubic equation of state to repeat the process for a multi-component system. So we can do flash calculations, distillation, solid-liquid equilibrium, vapor-liquid equilibrium. Any type of equilibrium can be made with the right particular kind of equation. So we'll notice, right, let's take a look at this chart right here. Hopefully it's not getting too busy quite yet. What is a defining characteristic of the critical point, right? What is unique about a temperature or pressure above the critical point?
It'll be a liquid.
Not a liquid. There's no difference between a liquid and vapor. It's a supercritical fluid. So above the critical point, it's not really a vapor, it's not really a liquid, it's supercritical. And so if we look at regions above the critical point here, all of the lines above the critical point will never have a region where this stability criteria is violated, which means that a cubic equation of state will show us that you'll always have a stable fluid going from any path up here in the ideal gas regime to something over here, which is a totally non-ideal fluid, but you never have to undergo a phase transition. Conversely, if you start off somewhere down here, right, following along an isotherm, you're going to hit the binodal region, and you're going to have a phase transition, condense down to a liquid, and then you're going to be pressurizing that liquid further. So above the critical point, you don't have the inflection that is necessary to induce a phase transition. So that's why cubic equations of state are so cool. It's because they have this cubic S shape. Without that cubic S shape, you're doomed to never trying to predict a phase transition. So there's so much more behind an equation of state than just more accurately predicting the density of nitrogen in a gas cylinder, which is typically the extent of which where you kind of use an equation of state in the undergraduate curriculum. So there's a lot more to it than that. Okay, any questions on this? So we're going to expand on how we actually quantitatively accomplish this task on Friday. And then your homework, I think it might be this upcoming homework that I'll post soon, you have to take an equation of state and actually predict the vapor pressure. So I'll make you, actually, I'll make you develop this same chart here for a real fluid. Okay.
Was the homework posted today or Friday?
Probably not today, some point soon. Okay, so then the last criteria, I'm just going to talk about the third law of thermo really quickly. Kind of can be basically derived from the first and second laws and the stability criteria, where basically the third law states that S equals 0 at T equals 0. So if we were to cool something at constant pressure, we can write ds is equal to C sub P over T dt minus dV dt at constant P dP. Oops. Right, this term will go to 0. C sub P and C sub V both have to be greater than 0. And this is because of the stability criteria. So if we take the limit as t goes to 0 of ds dt at constant P, so just as a refresher here, so when we have this equation here, right, this is totally valid under all circumstances. So we can just magically say dt, dt, right? Because these total differentials are saying, you know, I don't care how this variable changes, just magically make it change. So in this particular case here, we're saying, oh, we're changing it by changing the temperature, and this term here cancels out and goes to 1. That's how we got to this equation down here. So ultimately, the final conclusion is that in the limit as t goes to 0, this goes to infinity. So if we look at a plot of the entropy versus temperature, it asymptotically approaches an infinite slope down there like this. But the end conclusion is that the temperature always has to be greater than 0, and you can never reach t equals 0. That's the end conclusion, which is basically just the statement of the third law. Okay. Any last minute questions? Thank you.